The self-information and the entropy are probably the most basic quantitative measures of information in the framework of information theory. They quantify, respectively, the information content of the event of a discrete random variable and the content of the information content of the random variable itself. In this video, we will introduce these quantitative measures of information. The self-information of the event of a random variable quantifies the information content of an event of this random variable, the information that is provided when we know that the random variable is equal to this event. We know a specific result for this random variable. For such a measure of information, there are several requirements. The first one is that the information must be a function of the probability of the event, and it must be a decreasing function of this probability, because the information that we have when we know that has happened something that has a high probability is lower than the information that we know that an event that happens in very few occasions has happened. Another requirement is that the information measure must be a continuous function of the probability. In practice, this means that if we have events with a similar probability, the information must be similar. And the final requirement is that if we have a joint event that joins two independent events, the event x equal to xi and y equal to yj, then the information must be additive. Taking into account that for independent events, the joint probability is equal to the product of the marginal probabilities, this means that the information measure must be additive under the product. With these requirements, the function that satisfies these requirements is the minus the logarithm of the probability. And this is the definition of the self-information of an event. Minus logarithm in a given base of the probability of the corresponding event. The base of the logarithm is defining the units of the information measurement. And the most common bases are base 2, and in this case the units are bits, and the Euler number. We have in this case the natural logarithm, and we have that the units are nuts. The entropy of a discrete random variable is a quantitative measure of information that is quantifying the uncertainty about the outcome of a given random variable. This uncertainty can be understood as the information of this random variable, because if we have an experiment, the higher the uncertainty, the higher the information that we get when we know the result. If we have a random variable with a given alphabet of mx symbols, and we know the probability of all these events, now the entropy is a very simple extension of the self-information. In fact, it is just the average of the self-information of the different events, of the different elements of the alphabet of the random variable. Taking into account the properties of the logarithm, we can have this minus the addition of the product between probability of each event times the logarithm of this probability. And if we change the sign from negative to positive, we invert the argument in the logarithm. This is because the basic properties of the logarithm. Here, by convention, we assume that 0 times logarithm of 0 is equal to 0. As with the self-information, the base of the logarithm is defining the units that we have for the entropy. If we use base 2, we have bits per symbol. If we use the Euler number, we have nuts per symbol. Given this definition, there are some bounds for the entropy, some limit values for this measure of information. The lower bound is 0, and entropy for a discrete random variable is non-negative. And the minimum value, 0, happens in the situation where we don't have uncertainty about the result of the experiment. The probability of an event is 1, and it's impossible to have as a result any other event. The upper bound is given by the logarithm of the number of events in the alphabet of the random variable. And this happens in the situation of maximum uncertainty about the result of the random variable. This happens when, a priori, all the events have exactly the same probability.